Okay, I think it's time to start. Today's speaker is Sergei Igonin from Yaroslavl, and he will speak about algebra and geometry of Lex representations and Bäcklund transformations from 1+1 dimensional partial differential equations and differential-difference equations. Okay, Sergei, you have 100 minutes.
100 minutes means until when? Until 21.
Until 21, yes.
Okay.
I ask everybody to switch off microphones, and we begin.
Okay. So first of all, I would like to thank the organizers for the invitation to give this talk. I will speak about some algebraic and geometric constructions related to partial differential equations and differential difference equations. First, we need to recall some notions from differential geometry. Well, consider a manifold E of dimension and a positive integer n. Then an n-dimensional distribution C on the manifold E is an n-dimensional subbundle of the tangent bundle of this manifold. So to define an n-dimensional distribution C on E, we choose an n-dimensional subspace CA for each in the tangent space at each point A of E, such that these subspaces CA depend smoothly on the point A. And a submanifold, we need also integral submanifolds. A submanifold S is an integral, is called an integral submanifold of the distribution if this submanifold S is tangent to the subspaces CA for all points A. Now, the following geometric approach to partial differential equations is quite well known and is quite useful, as we will see. So, for any PDE satisfying some non-degeneracy conditions, we will define a manifold and a distribution such that solutions of the PDE correspond to n-dimensional integral submanifolds. The number n is the number of independent variables in the PDE. The manifold E and the distribution C are constructed by means of the theory of infinite jet bundles, and I will explain what this means. And this approach goes back to the classical works of Sophus Lee and Elie Cartan, and the distribution C is called the Cartan distribution. And this approach turned out to be particularly useful in the study of integrable PDEs, or especially soliton equations, because it is known that symmetries that many structures related to integrable PDEs, such as symmetries, conservation laws, Bäcklund transformations, and Lex representations, can be studied geometrically in a coordinate independent way using this approach. And I will present a development of this approach related in order to obtain new results on Bäcklund transformations. Now I can give a summary of the main ideas of my talk. So we regard a PDE as a manifold with a distribution. Solutions of the PDE correspond to integral submanifolds. Now, so we have this geometric approach to PDEs. So one can try to define geometric invariants for PDEs using this manifold E and the distribution C, and this is indeed possible. Well, recall that for any topological space X and each point A, we have the fundamental group pi1 of the space X at the point A. And in a somewhat similar way, I will define an analog of fundamental group for points of a PDE E. Well, here I say for any analytic PDE, well, actually, many results remain valid also in the smooth case, but the smooth case requires some technical modifications, which I don't want to discuss today. So for simplicity, in my talk, I consider only analytic PDEs. So for each point A of a manifold of the manifold E corresponding to a PDE, I will define a so-called fundamental Lie algebra, which will be an analog of the fundamental group. So the main results or ideas about fundamental Lie algebras are as follows. These Lie algebras are new geometric invariants for PDEs. Computing these algebras, we get interesting infinite dimensional Lie algebras. For instance, infinite dimensional subalgebras of Kac-Moody algebras, and appear in this picture also infinite dimensional Lie algebras of certain matrix valued functions on some algebraic curves. And the computations of the explicit structure of the algebras have been done in collaboration with Gianni Manna from Torino. Next, using fundamental algebras, one can obtain new results on Bäcklund transformations and zero curvature representations, which are also called Lex representations. And now, what is the main idea behind the definition of fundamental algebras? Recall that the classical fundamental group can be defined by means of so-called topological coverings of X. So in topology, there is a notion of coverings, which are bundles with discrete coverings. Topological coverings are locally trivial bundles with discrete fibers. And the fundamental group, the standard definition of the fundamental group uses homotopy classes of loops, but it is also possible to define the fundamental group by means of topological coverings. We will recall this approach. So in order to define the fundamental Lie algebra for a PDE, one can try to develop a theory of coverings of PDEs, and this is indeed possible. There is a notion of differential coverings for PDEs, which can be used in order to define fundamental Lie algebras for PDEs. So let us see what are differential coverings of PDEs. First, before doing this, I will summarize some applications of the fundamental Lie algebras in the case of 1+1 dimensional evolution PDEs. So in this approach, we obtain the following results. Necessary conditions for existence of a Bäcklund transformation between two given PDEs. Necessary conditions for existence of a non-trivial zero curvature representation for a given PDE. And these necessary conditions really work. In particular, they allow us to prove non-existence of Bäcklund transformations for some pairs of PDEs and non-existence of non-trivial zero curvature representations for some classes of PDEs. And I would like to emphasize that we consider the widest class of Bäcklund transformations, which are not necessarily of Miura type, and the widest class of zero curvature representations, which may depend on derivatives of arbitrary finite order. In particular, the order of derivatives in the zero curvature representations and Bäcklund transformations can be in principle higher than the order of the initial PDE. Also, in order to obtain these results, we develop some technique which gives a byproduct, which may the following byproduct, which may be of independent interest in my opinion. Namely, we find a normal form for zero curvature representations with respect to the action of the group of local gauge transformations. So we consider we fix a 1+1 dimensional evolution PDE and consider all zero curvature representations of it. One has the group of local gauge transformations acting on the set of zero curvature representations, and we find a normal form for zero curvature representations with respect to this action. Also, we get invariant meaning for infinite dimension for some infinite dimensional algebras and algebraic curves related to some PDEs. So now, what are differential coverings? This notion was introduced by Alexander Vinogradov and developed in 1980s and developed by Alexander Vinogradov and Joseph Krasilchik. So let me show you first a classical example. We consider the KdV equation and the modified KdV equation and the Mura transformation, which is a map from solutions of mKdV to solutions of KdV. So if V is a solution of mKdV, then U given by this formula satisfies the KdV equation. And right, this is the first property. So for any solution V of mKdV, U given by the formula is a solution of KdV. And another property which we need is the following: if we fix a solution U of KdV, we can study its pre-image under this map, and the pre-image of every fixed solution U of KdV is a one-parameter family of solutions V of mKdV. So if we fix a function U satisfying KdV and consider the system of these two equations, this equation and this equation, this system has a one-parameter family of solutions. Now, an informal description of differential coverings in coordinates is a generalization of this example. So first I give this informal description in coordinates, and in a few minutes I will present a geometric coordinate independent definition. But now let's consider the coordinate description. We have one PDE here with independent variables xi and unknown functions u. So any number of independent variables and a vector u of unknown functions. Here we have a PDE E2 with independent variables yi and a vector of unknown functions v. Well, the number of unknown functions can be arbitrary. The PDEs can be also basically arbitrary. In particular, they may be overdetermined, but must be consistent. What is important is that the number of independent variables is the same here and here. And we consider the map from solutions of E2 to solutions of E1 given by this kind of formulas. Here, the right-hand side can depend on yi, v, and any finite number of derivatives of v, also here. And so for any solution v of this of E2, u and xi given by these formulas determine a solution of E1. And another property similar to the above example is the following: if we fix a solution u of E1 and study its pre-image under this map, this pre-image is a family of solutions of the PDE E2, a family depending on a finite number d of parameters. In the geometric definition of coverings, which I will define in a few minutes, this number d will be equal to the dimension of fibers of the covering. Right. So we consider we require that the number D is finite, which means that we consider coverings with finite dimensional fibers. This class of coverings is sufficient for applications to Bäcklund transformations and zero curvature representations of 1+1 dimensional PDEs. And this class of coverings is rich enough, as we will see. But in principle, coverings with infinite dimensional fibers also have applications which you can see quite often at this seminar, but not today. So just to since this is quite important, this information is quite important for the talk, I would like to recall the basic ingredients. We have a map from solutions of E2 to solutions of E1 given by this kind of formulas. The right-hand side can depend on independent variables, dependent variables, and any finite number of derivatives. And so any solution V is mapped to of E2 is mapped to a solution of E1. And what is important also is that for a fixed solution U, its preimage is a family of solutions of E2 depending on a finite number of parameters, which means the following. If we fix a function U of xi satisfying the PDE E1, we can consider this system of equations. We consider this equation. So the function U is fixed. So we know the x for any xi from some open subset, we know the values of U. So we consider this equation, and this, which and each of them is a vector equation. And this system of equations has a family of solutions depending on a finite number D of parameters. All right. So this is a differential covering in coordinates. Now, how? Right. So now, how Bäcklund transformations can be described using this language? Suppose that we have two PDEs, E1 and E2. One says that E1 and E2 are connected by a Bäcklund transformation if there is another PDE E3 and a pair of coverings from E3 to E1 and from E3 to E2, such that such a pair of coverings, and then we can obtain solutions of E2 from solutions of E1 as follows. We take a solution of E1, find its preimage in E3, and project it to E2. And also, similarly, we can obtain solutions of E1 from solutions of E2. We take a solution of E2, find its preimage here, and project to E1. Another well-known example, we consider the case when E1 is KdV, E2 is also KdV, and E3 is this equation where lambda is a constant. And we consider two coverings from this equation to KdV, this covering and this covering. They are slightly different. And one can do the following. We can take the trivial, as a starting point, we can take the trivial solution U equal to a constant, take it here, and find its preimage. Which means that we need to solve for U equal to a constant, we need to solve this system of two equations. It's possible, and then as a result, one obtains a parametric family of solutions of this equation. Then we project this family of solutions back to KdV by the second covering, and we get a family of solutions of KdV which contains in particular the one soliton solution. Now we can take the one soliton solution, substitute it here, find its pre-image under the first covering, and we get a family again of a parametric family of solutions of this equation. Projected by the second covering, we get a bigger family of solutions of KdV, which contains in particular the two soliton solution, and so on. Iterating this procedure, one can obtain all multi-soliton solutions of KdV and many other interesting solutions. So now we introduce some geometry. As I said, for a PDE can be regarded as a manifold with a distribution. So let us discuss how to define a manifold and a distribution for a given PDE. It's the main idea can be understood from the following example. We consider the manifold E is called the infinite prolongation of a PDE. So let us define the infinite prolongation of the KdV equation. In the case of KdV, the infinite jet space is the infinite dimensional manifold with these coordinates. So now x, t, u, ux, ut, and so on, all partial derivatives of u, all of them are regarded as formal variables which play the role of coordinates for this infinite dimensional space. So, so J infinity is the infinite dimensional space with these coordinates. We have the total derivative operators. The structure of them is very simple. We have GDEq term here. Here now we have d over du and ux. We add x to u. Here we have ux, uxx, ut, uxt. So in the coefficient we add x. And similarly here, in the coefficient we add t. So these two expressions are well known as total derivative operators, and in the geometric picture they are regarded as computing vector fields on the manifold J infinity. Now we take the KdV equation and we differentiate it with respect to x and t any finite number of times. So first, if we differentiate KdV with respect to t, we get this equation. Differentiate with respect to x and get this equation, and so on. We differentiate KdV with respect to x and t any finite number of times. As a result, we get an infinite collection of algebraic equations in those variables. So we can consider the algebraic variety here in this space determined by this infinite collection of algebraic equations, and this algebraic variety turns out to be a non-singular manifold, and the vector fields dx and dt are tangent to this submanifold E and span a two-dimensional distribution on it called the Cartan distribution. Similarly, for any PDE satisfying some non-degeneracy conditions, with n independent variables, one can construct a manifold E with an n-dimensional distribution C called the Cartan distribution. And in this picture, solutions of the PDE correspond to n-dimensional integral submanifolds of the distribution. Okay, now a geometric definition of coverings. We have two PDEs, E1 and E2 are manifolds. C1 and C2 are the corresponding Cartan distributions. We consider a smooth map tau from E2 to E1, and it is called a differential covering if two properties hold. Tau, first, tau is a bundle with finite dimensional fibers. well, no, not more, well, several properties called. So tau is a bundle. Tau star is the differential of this bundle. So it is a smooth, it is a map from the tangent bundle of E2 to the tangent bundle of E1. It must preserve the Cartan distribution. And moreover, for each point A of E2, the restriction if we restrict tau star to the corresponding subspace of the Cartan belonging to the Cartan distribution, we get a linear map from this space to this space, and it must be an isomorphism. So this is the well, if tau satisfies these properties, then it is called a differential covering. Now, why we use the word covering? Why Vinogradov and Krasilchik, who introduced this, well, Vinogradov introduced, I think, Vinogradov introduced this definition. Why he called such maps coverings? The reason is that they are a generalization of standard of classical topological coverings. Namely, let us consider the degenerate case when the Cartan distribution is the whole tangent bundle. Then what is tau? Then tau is a bundle which is an isomorphism of tangent spaces, and such a bundle must have discrete fibers, so it will be a topological covering. So in the degenerate case, when the Cartan distribution is the whole tangent bundle, these differential coverings are topological coverings. But in general, the Cartan distribution is much smaller than the whole tangent bundle, and because of this, one has much more differential coverings than topological coverings. Now, recall that topological coverings of a manifold M are determined by actions of the fundamental group of the manifold. And we want to introduce an analog of the fundamental group for differential coverings of PDEs. And it is possible, as I will show you. And as a result, the precise definition of the resulting concept I will give later. And first, I would like to describe some properties of it. First of all, in topology, we get the fundamental group, which is a group. And here we have the fundamental Lie algebra, which is a Lie algebra, not a group. Why we get a Lie algebra instead of a group? The informal explanation is the following. In topology, topological coverings have discrete fibers. So because of this, the fundamental group is a discrete group. For PDEs, differential coverings, fibers of differential coverings are manifolds. So one can expect that, and we get an action of our fundamental group or algebra on the fibers. So since fibers are manifolds, one can expect the fundamental group of a PDE to be a Lie group. Moreover, the structure of differential coverings is so rich that one can expect an infinite dimensional Lie group as a fundamental group for PDEs. But it is not convenient to work with infinite dimensional Lie groups. Well, it's in the case of infinite dimensional setting, it is much more convenient to work with Lie algebras instead of Lie groups. So Lie groups are replaced by Lie algebras, which means that we study local geometry of differential coverings. And for differential coverings, local geometry is rich enough, as we will see. So we study things locally, and because of this, groups are replaced by Lie algebras. The first property, as I said, the definition will be given later. First, I describe some properties of fundamental Lie algebras. First, for any differential covering from E prime to E, the fundamental algebra of E at the point A acts on the fiber over this point. The fiber is a finite dimensional manifold, and recall that an action of a Lie algebra on a manifold is a homomorphism from this Lie algebra to the Lie algebra of vector fields on the manifold. Okay, next property. So first, to describe the next property and its applications, we recall a well-known property of topological coverings. If we have a topological covering tau from M prime to M, then and we take a point A prime of M prime and consider its image in M, then we get this embedding of groups. The fundamental group of M prime is embedded to the fundamental group of the base manifold M. For differential coverings and fundamental Lie algebras, one has a similar property. We take a differential covering, point A prime in E prime and its image in E. Then the fundamental algebra of E prime at A prime is embedded to this fundamental algebra of E, and this embedding is of finite codimension, and the codimension of the embedding is equal to the dimension of fibers of the covering tau. So we see the following: the fundamental algebra of E prime is isomorphic to a subalgebra of the fundamental algebra of E, a subalgebra of finite codimension, where the codimension is equal to the dimension of fibers of the covering. Now let us see an application of this fact. Suppose that we have two PDEs, E1 and E2, connected by Bäcklund transformation. So we have this diagram of coverings. We take a point A3 in E3, consider its images, its image in E1 and its image in E2. Then by the above property, we now we consider the fundamental algebra of E3 and the algebras of E1 and E2 at those points. By the above property, we get an embedding of the fundamental algebra of E3 to that of E1, and an embedding of the fundamental algebra of E3 to that of E2. And both embeddings are of finite codimension. Therefore, these two fundamental algebras have a common subalgebra of finite codimension. But the algebras themselves, in the case of, for instance, in the case of soliton integrable 1+1 dimensional PDEs, those fundamental algebras will be infinite dimensional. And we see that these infinite dimensional algebras have a common subalgebra of finite codimension. Therefore, they cannot be arbitrary. They must be very similar. We get here two infinite dimensional algebras which have a common subalgebra of finite codimension. This is a powerful necessary condition for existence of a Bäcklund transformation between E1 and E2. So the necessary condition reads as follows: if E1 and E2 are connected by a Bäcklund transformation, then the fundamental algebra of E1 and the fundamental algebra of E2 have a common subalgebra of finite codimension. Now, I would like to say a few words on the structure of those algebras in the computed examples. Together with Gianni Manna, we have considered a list of equations which include some well-known PD 1+1 dimensional PDEs, such as KdV, nonlinear Schrödinger, Novikov, and Landau-Lifshitz. In those examples, the main part of the fundamental Lie algebra is turns out to be an infinite dimensional Lie algebra of certain matrix valued functions on an algebraic curve. In particular for KdV and NLS, the curve is rational, that is, it is of genus 1. And for Novikov and Landau-Lifshitz equations, the curve is of genus 1, so it is an elliptic curve. Well, this is not surprising, of course. This is closely related to the fact that those PDEs have zero curvature representations with parameters lying on those curves, but the explicit zero curvature representations are defined in coordinates, and here we have a coordinate independent approach, which allows us to recover the curve for those to recover algebraic curves for those PDEs in a purely geometric way, not using any coordinates. Okay, and using the above necessary conditions for existence of a Bäcklund transformation, we get the following application, which I find quite interesting. Let E1 and E2 be some PDEs from those examples. As I said above, we get some algebraic curves related to those PDEs, related in an invariant way. Then the following statement is valid. So we consider two PDEs. If the corresponding algebraic curves are not birationally equivalent, then there is no Bäcklund transformation between E1 and E2. So the statement is valid for all those examples. In particular, we see that KdV and non-singular Novikov are not related by Bäcklund transformation, because here we get the rational curve and here the elliptic curve. Also, NLS equation, nonlinear Schrödinger equation, and non-singular Landau-Lifshitz are not connected by any Bäcklund transformation for the same reason. So, as I said, we get invariant meaning for algebraic curves related to those PDEs. And so those examples have been studied in detail, but it is clear that similar results can be obtained also for many other 1+1 dimensional evolution PDEs. For instance, the Kaup, Cooper-Schmidt, and Sawada-Katera equations, which are of order 5. Now, the main I would like to explain the definition of fundamental algebras, or skipping some technical details, but presenting the main idea. In order to explain the definition of fundamental algebras, we need first to recall some well-known property of topological coverings and the classical fundamental group. Namely, we consider a topological space M, or for simplicity, a finite dimensional manifold M, and a point A of M. And now we will recall how one can define the fundamental group of this manifold at the point A, using only topological coverings of M without using loops in M. First, let us recall the relations, some relations between the fundamental group and topological coverings. We consider all coverings tau of M, and we take an element G of the fundamental group. Since the fundamental group acts on the fiber, each element G gives a transformation G tau for the of the fiber over the point A. Okay, and now let us consider two coverings, tau1 and tau2, over the same base. And here phi is an arbitrary continuous map such that the diagram is commutative. Then for any such commutative diagram, one has the following relation for the corresponding transformations. So we have the transformation g tau of the fiber of the covering g tau1 this is a transformation of the fiber of the covering tau1. This is transformation of the covering tau2. Those transformations correspond to the fixed element g, and we restrict phi. We restrict our continuous map phi to the fiber of tau1, and as a result, and this relation is valid, which is easy to check. Okay. Now, what is important for us is that any element G of the fundamental group is uniquely determined by the following collection of transformations. We consider all coverings tau of M, and for each covering tau, we consider the corresponding transformation G tau of the fiber. So for each covering, we have a transformation. So we have an infinite collection of transformations G tau, and this infinite collection of transformations determines uniquely one element G of the fundamental group. Now we do the following, which is well known. We give an alternative definition of the fundamental group as follows. By definition, we consider an element of the fundamental group is a collection of such transformations for all coverings tau satisfying property 1. So this is a very important point of my talk. So I would like to repeat and explain in more detail. Well, so for what we do here, so we give the following non-classical definition of the fundamental group. Although this definition is non-classical, it is of course known to specialists. So in order to define one element of the fundamental group, we specify a transformation G tau for every covering tau. So for every covering tau, we choose a transformation of the fiber. We call it G tau, and we require that for any commutative diagram like this, where tau1 and tau2 are coverings and phi is an arbitrary continuous map, one must have this property. So if this infinite collection of transformations satisfies this property for any commutative diagram, then one can say that this collection is admissible, and this infinite collection of transformations is called an element of the fundamental group. Okay, now what is the group operation? Well, it's easy to understand. The group operation is given just by composition of those transformations G tau. And right, and one can check that as a result, one gets some group, and one can easily check that the resulting group is exactly the fundamental group. And this works for any manifold M, which can even be non-connected. So in principle, M may have several connected components. Never mind, the approach works if we fix a point A, and consider this a group defined in this way, it will always be exactly the fundamental group. Okay, now we use a similar approach in order to define fundamental algebras for PDEs. The main idea is that we consider an infinitesimal version of the above approach. So here, G tau is an invertible transformation of the fiber, and now we replace invertible transformations on fibers by vector fields on fibers. Then what happens with the what changes? So first I give a main idea, I give an informal explanation revealing the main idea, and then I will add some more technical details. So what we do, we consider all differential, we fix a PDE E, we consider all differential coverings of it, all differential coverings tau of it, and for each covering tau, we specify a vector field on the fiber. We choose, we take E is fixed, and also a point A of E is fixed. So for each covering tau, we specify a vector field G tau on the fiber. And we require the following: for any commutative diagram like this, where tau1 and tau2 are differential coverings and phi is any analytic map, the following property, the following relation must be valid. The differential of phi must map the vector field G tau1 to the vector field G tau2. It's easy to see that this property is the infinitesimal analog of this property. Okay, this is and now then now one can try the following definition of the fundamental algebra. An element of one element of the fundamental algebra is determined by the following infinite collection of vector fields. So we specify, we consider for each covering, we specify a vector field G tau on the fiber, and those vector fields must satisfy this property for any commutative diagram. Okay, so one element of the fundamental algebra is such an infinite collection of vector fields. The Lie bracket is then given by the usual commutator of vector fields. So as a result, one gets a Lie algebra. All right, this is the main idea. But in order to give the precise definition, I add the word formal, which roughly speaking means the following. When we speak, we consider not only small differential coverings, but also so-called formal differential coverings, which roughly speaking means that we replace analytic functions by formal power series. And then it is natural to replace Lie algebras of vector fields on fibers by arbitrary Lie algebras. And as a result, one gets, if one writes down everything properly, one gets so-called formal zero curvature representations, which I will consider in examples on the next slides. But but the main, in order to understand the main idea, you do not need to go into those technical details. So the main idea is, as I explained, for every differential covering we have, so one element is determined, one element of the fundamental algebra is determined by infinite, corresponds to an infinite, to the infinite connection of vector fields where we have a vector field on the fiber of each covering, but actually we consider not only analytic coverings but also formal differential coverings, which roughly speaking means that we switch from analytic functions to formal power series and from Lie algebras of vector fields to arbitrary Lie algebras. Okay, so what are so as I said, formal differential coverings correspond to so-called zero curvature representations. So let us discuss zero curvature representations. Let's consider an example. We have here a scalar 1 + 1 dimensional evolution PDE for a function u of two independent variables x and t. So we have a PDE of this form. Ut is derivative with respect to t, and on the right hand side the function f may depend on xt and arbitrary derivatives of u with respect to x. Now for any vector space we consider the Lie algebra of linear maps and the group of invertible linear maps and functions a and b with values in the Lie algebra of all linear maps. One says that the functions a and b form a zero curvature representations if the following well-known equation is valid, where dx and dt are the total derivative operators. Now, we need also so-called gauge transformations. A gauge transformation is given by a function g with values in the group of invertible linear maps, and if we have a zero curvature representation given by a and b and a gauge transformation given by g, we can produce a new zero curvature representation given by functions a tilde b tilde, which are written here. So we initially have functions a and b, we apply and a function g which is invertible, we apply g to a and b by these rules, we get functions a tilde and b tilde, which also satisfy the zero curvature condition. They form a zero curvature representation, which is called zero gauge equivalent to the initial zero curvature representation. Okay. So it's easy to check that this is in this way we get an action of the group of all gauge transformations on the set of zero curvature representations of a given evolution equation. Now, for such an evolution equation, the corresponding manifold E will be a manifold with the coordinates x, t, uk, where uk corresponds to k's derivative of u with respect to x. Now, so we have the action of the group of gauge transformations on the set of all zero curvature representations. So one and right, so it's it determines an equivalence relation of the set of zero curvature representations. Two zero curvature representations are called gauge equivalent if there is so this a tilde, the ZCR a tilde b tilde is called gauge equivalent to the ZCR a and b, to the ZCR a b if they are related in this way by means of some gauge transformation. This is indeed an equivalence relation on the set of zero curvature representations. Right. So two zero curvature representations are gauge equivalent if they lie in the same orbit of the action of this action of the group of gauge transformations. Okay, now one can try to use gauge transformations in order to simplify the form of a given zero curvature representation. So one can try to find, so since we have an action of the group of gauge transformations on the set of all zero curvature representations, one can try to find a normal form for zero curvature representations with respect to this action. So, right, so everything is done on a neighborhood of a fixed point A of the manifold E. Let us, for simplicity, consider this point which is determined by where all coordinates of the manifold are 0. Then the following fact is valid. We start with an arbitrary zero curvature representation. So we start with an arbitrary zero curvature representation AB. We apply applying a suitable gauge transformation, we get A tilde and B tilde satisfying these three conditions. So we have the zero curvature condition, which is not surprising, but also we get some extra conditions. So from an arbitrary zero curvature representation AB, which was required to satisfy only this zero curvature condition, after applying a suitable gauge transformation, we get A tilde and B tilde satisfying the zero curvature condition and some extra conditions, which are written here. And this is a normal form for zero curvature representation with respect to the action of the group of gauge transformations. Here I consider, for simplicity, the case of a scalar equation, but a similar approach works also for multi-component equations. Okay, now we do the following. In the previous slides, I explained a geometric definition of the fundamental algebras for PDEs. It's nice and coordinate independent, but it is not convenient for computations. Well, that definition may look rather abstract because we use some infinite collections of vector fields. And in order to make actual computations, we give another definition which is equivalent to that geometric one. So the strategy is the following. We have the geometric definition of fundamental algebras, which was explained. It works for all PDEs. And now we give an alternative coordinate definition for 1+1 dimensional PDEs. This definition of fundamental algebras, which I am going to explain in the next slide. So this alternative definition, it depends on it uses a particular system of it uses this particular system of coordinates of the manifold E, but it can be shown that it is equivalent to the above geometric definitions. So the geometric definition works for any PDE, but in the case of 1+1 dimensional evolution PDEs, we get also an alternative definition of the fundamental algebra, which is equivalent to the geometric one. And this alternative definition, relying on some coordinates, it is much more convenient for explicit computations. So what is the alternative coordinate definition of fundamental algebras in the case of 1+1 dimensional evolution PDEs? Right. So we have this normal form of zero curvature representations. We consider Taylor series of the functions A tilde and B tilde. So we view A tilde and B tilde as power series in the variables x, t, u, k. We regard the coefficients of this power series as abstract symbols, and we introduce the following Lie algebra. FPEA is the Lie algebra generated by those coefficients regarded as abstract symbols. So the coefficients of the power series A tilde and B tilde are generators of the Lie algebra, of this Lie algebra, and relations for the generators are provided by all those equations. Okay, so as a result, we get the Lie algebra FPEA given given in terms of generators and relations. Okay. All right. This construction immediately implies that representations of this Lie algebra classify up to gauge equivalence zero curvature representations of this form, where A may depend on x, t, u, and so on up to up, where up is the derivative of u of order p with respect to x. All right. So as I said, I explained here the case of scalar equations, but everything works for multi-component equations as well. So we get, as a result, we get a surjective sequence of homomorphisms of Lie algebras, a sequence of surjective homomorphisms of Lie algebras. And it turns out that the fundamental Lie algebra of the evolution PDE is isomorphic to the inverse limit of this sequence. And this, in many cases, this allows to compute the explicit Lie algebra of the explicit structure of the fundamental Lie algebra, because each term in this sequence is a Lie algebra given by generators and relations, and those relations can quite often be written down explicitly and turn out to be not, one can see some structure in them, and as a result, one can recognize some known Lie algebras in those. So one can prove that one can quite often compute the explicit structure of those Lie algebras. Okay, so as I said, the Lie algebra FPEA is responsible for zero curvature representations of this form, where A may depend on x, t, u0, u1, and so on up to up. But one can consider a much smaller class of zero curvature representations, when A depends only on u0, then. And moreover, if the initial equation does not depend, if xt do not appear here, then one can consider this class of zero curvature representations, which is relatively small. Then this class can be described similarly by means of representations of the so-called Wolke-Sestabrook prolongation Lie algebra, which was invented by Wolke and Estabrook in 1970s, I think. But this Lie algebra does not have any coordinate independent meaning, and in order to define the prolongation Lie algebra, Wolke and Estabrook did not use any gauge equivalence. So because of this, their method cannot be extended to the case of more general zero curvature representations of this type. Okay, now some applications. Recall that a PDE is called S-integrable if it is integrable in the sense of soliton theory, which means that it is integrable by the inverse scattering method, relying on zero curvature representations and Bäcklund transformations. Then for such a PDE, the above Lie algebras must have the following property. There are P and A such that this Lie algebra is infinite dimensional and is not solvable. This is the requirement. Why those two requirements? The informal explanation is the following. It is not solvable because it is known. It must not be solvable because it is known that zero curvature representations with values in solvable Lie algebras cannot establish S integrability, and it must be infinite dimensional because one needs a parametric. One needs zero curvature representations with a so-called spectral parameter, and a spectral parameter must be non-trivial. And this means that, and if we switch to the Taylor series with respect to the spectral parameter, we get a zero curvature representation with values in an infinite dimensional Lie algebra. Okay, right. So these properties give a necessary condition for S integrability of a given PDE, namely that if E is S integrable, then there are P and A such that this Lie algebra is infinite dimensional and is not solvable. And I would like to emphasize that this approach is applicable to all S integrable PDEs, including PDEs which do not possess higher local symmetries or conservation laws. So when one has an integrable evolution equation, one can look for higher local symmetries and conservation laws, and quite often one finds hierarchies of symmetries and conservation laws, but not always. It is known that there are S-integrable evolution PDEs which do not possess any higher local symmetries or conservation laws. So right, so therefore the existence of high symmetries or conservation laws cannot be taken as a necessary condition of S integrability. And here in this approach works for all S integrable PDEs because it is designed so that it captures exactly the essence of S integrability. Okay, and now some applications. So we have, recall that we have this infinite collection. We have this sequence of surjective homomorphisms of the Lie algebras FP, and quite often one can find a number Q such that the surjective homomorphism from FP to FQ has a solvable kernel. Then if FQ is solvable, then the equation is not S integrable because all those algebras FP will be solvable as well. And now an explicit example. Consider this family of equations. We have here Q. It can be shown that one can take Q equal to 1 here, and as a result, as a consequence, one gets the following result. If here we have arbitrary function f. If the third order derivative of f with respect to u3 is non-zero, then this algebra is nilpotent for all p, and the equation is not S integrable. More explicitly, this means the following: if this holds, then any zero curvature representation of this equation is gauge equivalent to a zero curvature representation with values in a nilpotent Lie algebra, and therefore this equation cannot be S integrable because a zero curvature representation with values in a nilpotent Lie algebra cannot establish S integrability. Okay. Now a few words about the structure of those algebras FT, EA for the studied examples. If we so solvable ideals, so for main applications, solvable ideals of those algebras can be ignored basically, and if we kill all solvable ideals of the algebra in those examples, we get the algebras of SL2 valued and SL3 valued functions on algebraic curves, rational curve for KDV and NLS, elliptic curve for Kirchhoff-Novikov and Landau-Lifshitz. Again, this is not surprising because those equations possess zero curvature representations with parameters lying on those curves. But here we get again a geometric coordinate independent meaning of the curves. Okay, and in the computation we used some results of people from a few people from the Netherlands on the Walquist-Estabrook prolongation algebras. Okay, now an example of a multi-component PDE. So the classical Landau-Lifshitz equation is an equation for a three-component function, such that for a three-component function, for a three-component vector of norm 1. And there is an m-component generalization of the Landau-Lifshitz equation for arbitrary m. It possesses a zero curvature representation parameterized by the following algebraic curve. All right, and now we together with Johann Mondeleur, Gianni Manna, and Vladimir Trushkov, we have obtained the following results on the algebras of FK EA for this PDE. Right. So F0 is isomorphic to the infinite dimensional algebra of certain matrix valued functions on the matrix valued functions on the curve 5, which is not surprising because this part L comes from the known zero curvature representation. But for k greater than 1, we get this surjective homomorphism. So again, we get this surjective homomorphism to this direct sum, where the L term is not surprising, and this term is, in my opinion, quite surprising. So the bold L comes from the known zero curvature representation, and this term is new to my knowledge. It does, at least this term does not come from the standard zero curvature representation. So we see that in the structure of those algebras, one can see not only the standard zero curvature representations, but also some new terms, some new non-trivial terms, which are non-solvable. So this is this algebra is not solvable. All right. And so, as I said, the algebras FKEA are given in terms of are defined in terms of generators and relations. And here I write down generators and relations for F0 of this PDE. The relations are quite beautiful in my opinion. And so starting from the PDE given by Golubchik and Sokolov, applying the described method, we get these relations. Not using any curve, we get this generators and relations of Lie algebra, and looking at those generators and relations, one can guess that one needs to consider this curve. Okay. Now some applications. So now a slightly different topic, but closely related to what I said above. Right. So our general strategy is to describe differential coverings by means of actions of Lie algebras. And as I said, we consider arbitrary differential coverings which are not necessarily of Miura type. Now I describe what happens when the covering is of Miura type. So Miura type, so-called Miura type transformations, also called differential substitutions, are a particular class of differential coverings. We have seen an example in the very beginning. The classical Miura transformation from MKdV to KdV is a Miura type transformation. Right. So we have a general strategy to describe differential coverings by means of actions of Lie algebras. One can ask what can be done for the particular class of Miura type coverings. And we have developed a method to construct and to classify, in some cases, Miura type transformations for 1+1 dimensional evolution PDEs of this form, where the right-hand side does not depend on x and t. So u is still a function of x and t, and uk is still the case derivative. But here, f does not depend on x and t. And we study Miura type transformations which do not change x and t. The method is a generalization of a result of Drinfeld and Sokolov on Miura type transformations for the KdV equation. Namely, well, in this very short paper, they did the following. They took the KdV equation and its lex pair, and without any proofs, they formulated how one can construct a lot of Miura type transformations for KdV using some algebraic and geometric manipulations with the lex pair, with the particular lex pair of KdV. Okay, now studying their results, I have developed the following generalization, and the idea is the following. We consider a PDE of the above type, so a PDE of this form, and a zero curvature representation where A and B are functions on E with values in a Lie algebra G. Okay, and also we consider an action of an action phi of the Lie algebra G on a manifold W. So phi is a homomorphism from G to the Lie algebra of vector fields on W. So this D of W is the Lie algebra of vector fields on the manifold W. Then one gets the following differential covering. So we start again. We start with the PDE E, zero curvature presentation, a homomorphism phi. Then we get this differential covering. Here the base manifold is E, the covering manifold is E cross W. The total derivative operators on E cross W are these given by these formulas. So what I mean here, this manifold E cross W will be also isomorphic to the infinite prolongation of some PDE, and the total derivative of the PDE written in coordinates will look like this. So these are the total dx and dt are the total derivative operators of E, and phi of A, phi of B are vector fields, are some vertical vector fields. So the Cartan distribution on E cross E is spanned by these two commuting vector fields. The fact that they commute follows from this condition. Okay, so this construction is known, but what the key observation of the key idea of the method is to determine which homomorphisms correspond to Miura type transformations. So to determine in which cases this covering will be a Miura type transformation, and the situation is as follows: if E is a scalar equation, then any Miura type transformation over E is of this type, where G is equal to the Walker-Estabrook prolongation Lie algebra. So this allows us to get a classification. In principle, this allows us to describe Miura type transformations over a scalar equation of this form, to describe all Miura transformations over such an equation by means of some algebraic, by means of some Lie subalgebras of the Walker-Estabrook prolongation Lie algebra. I don't want to give all technical details which are written in this publication. Just the main idea is that we, using this approach, we switch from Miura. This approach allows us to switch from Miura transformations to some purely algebraic construction on the Walker-Estabrook prolongation Lie algebra. And the Walker-Estabrook prolongation Lie algebra can be computed explicitly quite often. And its subalgebras can also be described, and as a result, one can, in principle, give, in the case when everything is computed explicitly, one can get an explicit list of all Miura type transformations for a given equation. And for KDV, it's it has almost been done. So it is clear that this can be done explicitly and completely, and a very extensive list is already available, and it is known that this list is contains all Miura type transformations up to introduction of a potential, but to my knowledge, not a very explicit list of all transformations has not been written yet, but it is clear that this can be done using this method. So the most important Miura type transformations are listed in the paper of Dmitry and Sokolov. They do come, because they come from the standard Lex pair of KDV, but not all Miura type transformations of KDV are listed here, because not all of them come from the standard Lex pair of KDV. And this approach allows to list literally all Miura type transformations for KDV, and for many other evolution PDEs, it's clear that computations can be done explicitly, but it has not been finished yet. Okay, and in the case of so this is what happens for scalar PDEs. One can get in principle complete classification if the Lie algebras are described explicitly. For multi-component PDEs, evolution PDEs of this type, one gets construction of Muir type transformations. There is no proof that all Muir type transformations can be obtained in this way in the multi-component case, but at least one gets a rich construction which gives quite a lot of Muir type transformations for multi-component evolution equations. Okay, now a few words about the case of differential difference equations. So it turns out that some parts of this theory can be translated to the case of differential difference equations. We study differential difference equations of this form, where u is a vector function of an integer variable n and a real or complex variable t. The notation is as follows: ut is the derivative of u with respect to t. Ui is this thing. So we switch n by n plus I. And then this equation is actually it encodes an infinite collection of ordinary differential equations of this form. So n is an arbitrary integer. We have so for each n we have this function u of n t, which is a function of one variable t for a fixed value, and this is a function of one variable t. So this becomes an ordinary differential equation. So we have an infinite collection of ordinary differential equations for an infinite number of unknown functions. Now consider another differential difference equation of similar type, and a Muir type transformation from this equation to this equation is determined by an expression of this type, where such that if V satisfies this equation, then U given by this formula must satisfy the initial equation. So a natural generalization of the classical notion of Muir type transformations for PDEs. Now, look, what changes? Now we have here we have function of n and t, where n is a discrete integer variable. So there is no x. T is still here, but there is no x. So x, the continuous variable x, is replaced by the integer variable n. And because of this, the total derivative operator dx is replaced by the so-called shift operator s, which does the following. It replaces n plus by n plus 1 and ui by I plus 1 in all considered functions. Now, using this shift operator, one can give the following analog. One can define the following analog of zero curvature representations. We consider matrix functions depending on a finite number of the variables ui, and a complex parameter lambda. And we suppose that M is invertible, and this equation holds as a consequence of 1. And what is 1? 1 is our initial differential difference equation. So this is an analog of the Lex equation or zero curvature equation for in the differential difference case. This is, of course, a well-known equation. And such pairs MU often arise from so-called Darboux transformations of PDEs. Because of this, it's natural to call them Darboux-Lax representations for the initial equation 1. And recall that for classical zero curvature representations, they are compatibility conditions for some auxiliary linear systems. Here, one also has an auxiliary linear system of this form where psi is an invertible matrix function. So you see that the differentiation with respect to x is replaced by the action of this shift operator s. So, and it is required that this overdetermined linear system for the matrix valued function psi is compatible modulo the initial equation 1. Okay. So I would like to outline some results. So we have translated some parts of the theory of coverings and Miura type transformations from the case of PDEs to the case of differential difference equations. The total derivative operators get replaced by the shift operator. So here dt remains because we still have the continuous variable t. Dx gets replaced by the shift operator s. And we have developed a method to construct Miura type transformations for differential difference equations using Lie group actions associated with Darboux-Lax representations. So recall that for Miura type transformations of PDEs, we had Lie algebras playing some role. So we had actions of Lie algebras, and here we get actions of Lie groups. And the reason is the following. The vector field dx gets replaced by the operator s, which is not a vector field, it is an automorphism of the corresponding algebra of functions. So dx was an infinitesimal automorphism, and s is a real automorphism of the algebra of functions of ui. And because of this, Lie algebras get replaced by Lie groups. Details of the method are available in this publication. Again, we considered with George Berkeley, we considered examples. Well, the list of considered examples includes these equations, and we have obtained new integrable nonlinear. Applying the method to these examples, we have obtained new integrable nonlinear differential difference equations connected with those equations by Miura type transformations. And I would like to conclude by an explicit example. Here, this is a quite well-known and celebrated equation, the so-called Narita-Ito-Bogoyevlensky lattice. So you see, this is a differential difference equation for a function u of an integer variable n and a continuous variable t. And here a new Miura type transformation for it. The covering equation is this one. This is a differential difference equation for a function v. And this is the Miura transformation. So for any non-negative integer p and any constants c1, c2, we have the following result. any solution V of this differential difference equation, U given by this formula satisfies the Narita-Ita-Bogayevlensky lattice. So this is a new Muir-type transformation for the Narita-Ita-Bogayevlensky lattice. Okay, I think I stop here in order to have some time for questions.
Thank you, Serежа. Questions, remarks? No? Okay, Serежa, thanks a lot again. It was quite interesting. Well, and this is our last meeting in the passing year, so I wish everyone a happy new year, and let's hope that the next year will be a little bit more, a little bit better than the passing one. Goodbye. Thank you for participating.
Thank you.